Remember from last class, what we talked about was there are alternatives to optimizing how you draw a line through a bunch of dots. And if you say, I want a straight line through those dots, the least squares fitting is the line out of all the lines, of all the slopes, of all the intercepts, that minimizes the squared distances vertically. So the distance vertically between all these dots in the line. If I square all those distances, that makes them positive, then we get the best fit. We get a line, and it's the one that, in some sense, it looks like the right line. However, if we actually mean the best line, the single best line, we have to actually have some properties about the data and the line relationship. One of them is that the residuals are normally or Gaussianly or bell-shaped in their distribution. We'll see how that plays out in a second. And that they have the same spread regardless of whether you look down at one end or up at the other end. So we're going to look through all these different cases through some data sets. Things that we might get wrong, someone mentioned in last class, if we had some data points that were far outside the data as it normally looks, then what we're going to see is a curve that gets dragged away towards those three blue dots at the top. Why? Because they're going to be the furthest from the line to get as close as possible to all the points with the square distance, magnifying that distance to those furthest points. And they actually have a surprisingly large effect on the overall fit. Even if there's lots of data, those points will have the most effect because they're furthest from the line, and you square those distances, it magnifies their effect. Other things that might happen might be a cloud of data that gets gradually more and more spread out. So when you fit this line, as we'll see, there's a little brother, big brother effect here. The things at this end have more effect on the curve because all these guys are well behaved. They all stay roughly close to the line because they're just not that spread out. Whereas the stuff at the upper end, it's more spread out, and because we have the squaring effect, this will tend to drag the line. The points at this end will have more effect on the fit than the ones at the other end, which just doesn't seem fair. Anytime we have some data playing more of a role in the calculation than others, it's a little dicey. It's a little suspect. So those are just some of the flavors of things that we might encounter. Let's take a look at a real-life analysis, which would be the quiz and exam grades. So we're going to go into here. We're going to open our W61. So here we're just loading our data. We're calling a variable called quiz, which will be all the elements in all the rows in the first column of this data set, and the test marks being the second column. And we can check that this makes some sense by looking at the Excel file, where we see, in fact, that scrolling up to the top, there's lots and lots of marks here. And somehow I've messed up my keyboard, so let's see how this works. The quiz grades are in the first column here. The exam marks are in the second column. So when we load into MATLAB, it ignores the headings, and we just assign those to representative names in this 2 lines here. We read in the whole thing. It'll be lots of rows by 2 columns, and we parse it out. We plot it. We make it look pretty with the title, and we're good to go. So this will take a second or two because reading Excel files is a bit slow, but there we go. We have our data. So quick quiz. If I'm trying to find this relationship between these data points, what was the menu trajectory to get to fitted lines and fitted curves for this? Where do we look? Tools, and then basic fitting. Tools, basic fitting. That's all you need to know. Tools, basic fitting. And the 2 main ones we're going to look at again will be linear and quadratic. And we talked a bit about the choice between those and the fact that if you're going to say quadratic is better, you have to have an argument that's stronger than the error or the residuals is smaller. If I choose a quadratic over a linear, the residuals have to be smaller. I'm using a more complicated function that's equivalent to a linear but with more stuff possible. So here we got into one of those dicey things where maybe linear was nice because it was simple, but somehow it didn't capture what happened at the bottom end here. Like we feel like there is kind of a swing shape to this. It doesn't look straight all the way through. So this is one of those problematic analysis questions. So what do we want to do with this? What's really representative of the data? And there's a few ways we could tackle it, and we talked about choosing between these last time. I'm going to talk about a different way today. Sorry, I want to do one extra addition here. Sorry, going back to Tools Basic Fitting. We were just talking about residuals, so I'm going to plot the residuals here, and it's going to yell at me for a perfectly good reason again. By default, the residuals, for some reason I don't understand, is defaults to bar plots, which is a little wrong, quite frankly, in my book. Usually, if the plot is a scatter plot, you want the plots of the residuals to be a scatter plot as well. So we just ignore the error here, and we say, oh, yeah, I want a scatter plot here. There we go. Now, this is also something that I have a bone to pick with MATLAB. It's a lovely tool, but it could add something to this graph down here that would make it easier to interpret. What is the most important line in the residual plot? What's the most important value? 0, yes. Because 0 means residuals are, what's the residual again? Pop quiz.
Distance from the best line.
Distance from the best line to your data points, exactly. So if everything was perfect, all these dots would be on 0 because your line and your data would be the same. But they're not, obviously. So what we're getting here along the 0 line is sort of the reference line. Anything above 0 on this bottom plot is data that's above the line. Now, which line are we talking about? Let's make this a little simpler to look at by only looking at, say, the linear. You can see that there is a cluster of points here, 3 of which are above 0. That corresponds, of course, to the 3 points here that are above the line. On the next point, we see 5 dots that are above the line, 5 dots above 0. When we look down at this end, we see that, oh yeah, there's a whole bunch of stuff below. Let's drag this out of the way. Well, actually, there's not that much. If you look at the right corner here, there's a little small number of things that are below 0, which is this line here, and most of it's above. So basically, we're subtracting away the line from the dots, and then we can see the above, over and under spread from this. Now, from this, we can definitely see that there's a trend. Or at least visually, there's an argument to be made that there is a trend. All the data at this end, or the preponderance of it, is above 0. That's bad. Down here, we also get a little sort of whoop of the bottom end where most things are above the plot here as well. That says that our best line fit is actually not going to be best in some way. Why? Because we're violating that. The errors will be normally distributed, which means evenly on either side of 0. And the spread's actually about the same. So the actual spread of these errors is pretty consistent from left to right. But there's definitely something not evenly distributed on either side of 0 that we can see in this. Sometimes it's a lot harder to see in the main plot. But just looking at this bottom end here, most of the data points in this whole range here are above 0. There's only a few that are below. That wouldn't be likely if the errors were actually normally distributed. There should be 50-50 chance of being above or below the line. If we flip to the quadratic, just for contrast, we see something that looks a little bit better. It's a little, again, sort of a judgment call. There's not a lot of data. But this line seems to have more things, about the same number above and below this line. I wish they'd just draw the line y equals 0 in here. But we also see something down here. Maybe there's something going on. Maybe it's not quite evenly distributed, but we're in the right ballpark. So this is where you get into arguments about goodness of fit and whether the fit's appropriate. All right. So one of the things that we said, if we're looking at quality of the fit, this is true or a problem for the linear fit to the quiz data. The scale of the residuals, it looks pretty much the same. If we look back at the plot, the spread, the vertical spread is roughly the same from left to right, so I'm okay with that. And are there any exceptional data points? There's a couple that are further away, but they're not wildly different, so that seems okay. But this is the checklist I go through when I look at the fit and whether a fit is a reasonable thing to be doing or whether the data needs to be cleaned up somehow.